All right, welcome to our Chapter 9 discussion here for our recorded lectures. So, this chapter, we're going to start talking about Vesper theory and something called polarity. Again, these are things you might be seeing in lab already a little bit as well. So, what these things are, we're going to start by focusing mainly on Vesper geometries first, and then use those to help us really figure out things like polarity. And what Vesper is really just an acronym that stands for valence shell electron pair repulsion. And really, it's kind of just a fancy way of saying that electrons repel each other. And so when we think about like how do we figure out the shapes of molecules, it's really all about spreading out electrons as much as we can. That's really kind of our main goal with all of these different shapes and all of these different geometries. We're just going to be working to spread out all of our electrons. And one of the things that I'll also mention a few times kind of as we go through this, a lot of our shapes are three-dimensional. Which means when we go to draw these on a 2D page, we want to have some way of kind of signifying that if we need to. And so I will show a few of those ways as far as how we can sketch some of these Vesper shapes as well. All right. Now, for our Vesper geometries, there are a couple different types, two in particular. We have what we call an electron geometry and also a molecular geometry. So first, for our electron geometry, this is going to be the geometry of everything around our central atom. So all of the lone pairs, all of the bound atoms, everything kind of included. Excuse me. For our molecular geometry, which is our kind of counterpart with this, this is going to be the shape of just all of the atoms arranged around our central atom. Lone pairs are still going to take up space, but when we look at the actual molecule, we're interested in just what's the general arrangement of the atoms. And that's going to give us what we call then our molecular geometry. And in general, we're always going to start by finding the electron geometry first and using that to find our molecular geometry. Now, if there are no lone pairs on our central atom, one of the things that will come out of that is that our electron and molecular geometries will actually be identical to each other. They will be the same. Now, one last bit of kind of terminology here that we'll kind of go over to help us with these electron and molecular geometries that I'll get to in a second. That's really going to come from Lewis structures, because it turns out in order to figure out anything about Vesper shapes, we actually have to have a correct Lewis structure first. And you're going to see a lot of chapters 8 and 9 really all build off of each other. If we can't draw a proper Lewis structure for something, then we can't figure out the right geometry. If we can't figure out the right geometry, we might not be able to get the right then kind of information about polarity or other things like hybridization. So drawing Lewis structures and doing all these things, they're really important because they kind of lead the next steps. When you get to 1212, it'll all lead to then something called intermolecular forces. And so it's a lot for us to kind of build on, but it's important because it's not really going to go away. Those intermolecular forces are something that show up in just about every other chemistry class you'll ever take. But the more you see it, the easier a lot of this stuff hopefully will get. So how do we go about finding these electron and molecular geometries, particularly electron geometry for kind of our starting point? What we're going to do is we're going to look for how many areas of electrons are going to be spaced out around the central atom in our geometry. So we're going to pick out our central atom, and then we're just going to count everything that's around it. Now, when we count these, what we're looking for in particular are going to be the total number of lone pairs plus the total number of bound atoms or bonded atoms. So as kind of a quick example, if I put CO2 up down here, looking at CO2, this carbon has 2 bound atoms and no lone pairs. So there's only 2 things around the carbon. The number of bonds does not matter, just the number of bound atoms. And the main reason for this is that when we're trying to figure out how many things are around our central atom, we're looking for how many areas of electrons are trying to spread out from each other. Well, there's a bunch of electrons collected in this double bond and a bunch of electrons collected in this double bond, but the electrons in the bonds aren't really spaced out very much. So it's the 2 kind of double bonds themselves that are trying to spread out as far as they can. So there's only 2 things spreading them apart. And the easiest way that's going to happen is if they go directly opposite of each other. And so when we go to figure out these shapes, our general kind of steps or the kind of the process we're going to go through is we're going to figure out how many things are around the central atom. And then from there, we're going to progressively go and figure out, okay, what's the now shape that those things are going to spread out into that maximizes how far they can spread out. And that'll give us our starting electron geometry for any molecule. And then from there, we can look at lone pairs and other pieces to find those molecular geometries. So what I'm going to do is actually just go through kind of each different electron geometry possibility and actually kind of show like how do we go from one electron geometry to another, and also how do we get the different molecular geometries from those electron geometries. So the first and kind of starting point for this is going to be if we have just two electron groups, or basically just two areas of electrons trying to spread out around one central atom. Right? And this is what we basically saw just a second ago with CO2. And what we're going to see is that our electron, and it turns out also our molecular geometry, will always be linear for this type of situation. If you only have two things that need to spread out around one atom, they can spread out exactly opposite of each other, which makes basically a kind of line type shape, which is why I refer to it as linear. All the names of these geometries are going to be, for the most part, mathematically based, as you see kind of their descriptions here that'll be coming up. So CO2 be an example of a linear molecule, both electron and molecular geometry. Now, going up to something that has two things around a central atom. So if we have two things we're trying, I'm sorry, not two, if we can go up to three things around a central atom, the most that we can possibly spread everything out is to make things kind of relatively flat, right? If we see our image over here, if we had something that was linear initially with things going kind of up and down, the biggest open space for new electrons is to come from a side, but if I put new electrons from the side, the electrons that were going up and down are going to get pushed away, and that's why we end up with kind of this, what we call a trigonal planar shape. So electron geometry for three things having to be spaced out around a central atom is always trigonal planar. And this is an example. This Lewis structure over here is for formaldehyde, right? Here's your Lewis structure, and there's kind of just a ball and stick model of it. The geometry around that carbon is trigonal planar, even though it has 4 bonds. Again, it's all about how many bound atoms there are really around it. Now, for molecular geometries, we have a couple different possibilities, right? If there's no lone pairs in the central atom, which is what we see here in formaldehyde, the molecular geometry is also trigonal planar. But as soon as we start adding lone pairs, that molecular geometry will change, right? Here we have an example of SO2, which does have a lone pair on the sulfur in this case. At least the way it does have a lone pair here. And so if we have a lone pair here, what's going to happen is we see just the shape of the atoms, right? We're not looking at the lone pair itself. So if we're looking for just the atoms in our structure, they make kind of this bent or kinked type shape. And that's actually what we refer to this in terms of kind of a geometry name. We'll actually refer to this as bent, and specifically we'll usually call it bent 120. We'll see why we specify the kind of degree angle of the bond here in just a minute. But we have a bent structure, and 120 is the approximate angle here, because if we have three things spread out in a flat kind of planar shape, the most they can spread out is about 120 degrees apart for each one. That would be kind of the general shape. So kind of 120 is the approximate angle, although usually this angle will end up being a little bit less, and we'll talk about kind of why that is here in a little bit as well. The last possibility, we don't see this one necessarily listed as a picture here on this page, if we add a second lone pair to our central atom, so imagine this being a lone pair also, if we just have the two atoms now that are bound to each other, now we're back to having something that's linear. And it turns out most of these geometries, if you add enough lone pairs, you actually can get back to linear for almost all except for octahedral. All right, moving up to having 4 electron groups. So if we think about, again, kind of the shape-wise, if I have a shape right here, so, and actually maybe this is the better one to look at, all my electron groups are spaced out as much as possible. The biggest empty spaces are on top or on bottom. So if I imagine trying to put electrons on top of the central atom right here, that's going to give me a new bond coming up to something, or like a lone pair up here. But all of these electrons that were going around here are again going to get pushed down, and now we get our first really, truly three-dimensional shape, right? We get something that looks like this, right? If we put that electrons on top, again, that trigonal planar pieces start getting pushed down, and we get what we refer to as a tetrahedral geometry. And again, the name tetrahedral comes from the fact that if we have kind of a 4-cornered polygon, what we have is a tetrahedron for its name. That's the kind of shape that we're creating there. Now, when we talk about electron geometries and molecular geometries, 4 things is always going to be tetrahedral for the electron geometry, and that's regardless of whether it's all bound atoms or, like, here's 3 bound atoms, 1 lone pair, 2 bound atoms, 2 lone pairs. All of those have a tetrahedral electron geometry because there's 4 total things around the atom. But for molecular geometries, then, our possibilities are going to be again, tetrahedral if there's no lone pairs, like methane that we see over here. If we had one lone pair, this is ammonia, if we're trying to look at ammonia shape, well, we have one atom that sits above all of the others, which are kind of in a triangular plane at the bottom. So it's kind of almost a pyramid type structure. And so with that one lone pair, we refer to this as trigonal pyramidal because we have a pyramid type structure with a triangular base. And then the last example down here at the bottom, we have water, which has two lone pairs. And for this, if we're trying to talk about its shape, maybe this isn't the best visual that they gave for this one, but it's kind of like a bent or kinked shape again. But the bond angle is different, right? And I know they give the bond angle for water over here. That's water in particular. But the actual bond angle for a normal tetrahedron, if it was something like methane, is 109.5. So we do refer to this as bent 109.5. So previously, the bent shape we saw was bent 120, because 120 is the approximate angle for trigonal planar. Here we see bent 109.5, because 109.5 is the normal angle for a tetrahedral shape instead. And again, we will usually see the real bond angles in those cases when we have those bent geometries being smaller than the names that are typically given. And that's just because these lone pairs, what's going to happen is these lone pairs take up a bunch of space. And because the lone pairs take up a bunch of space, more so than a normal bond, then we're going to see those bonds actually get pinched a little bit closer together. And we'll talk again about this in just a second because it's actually going to be really important to the next electron geometry in terms of how we figure out the molecular geometries we end up with. So to predict our next shape, if we start from tetrahedral and we want to add more things around our central atom, basically any spot that's immediately between any three of these things, so like coming in the face of our tetrahedron, like at an angle like here, or maybe from the side over here, probably the easiest one to see might actually be coming from straight up underneath between these three. If I put more electrons right here, these three that are going kind of pointed down are actually going to get pushed back up. And that's how we actually get to this shape that we're going to see for 5 electron groups, or 5 things around our central atom. So if we have a central atom, what we're going to have is what we refer to as a trigonal bipyramidal geometry, where we really have almost kind of 2 points that are in a linear component going up and down in what we refer to as axial positions. And then we also have 3 other atoms or just other things attached to our central atom going around what we call these equatorial positions. And so 5 total things. We have 2 different position types. This is the first geometry that does that. In fact, it's the only geometry that really does that. All of our other geometries, all the positions are equal to each other, right? If I back up for a second to a tetrahedral shape, like if I have a lone pair, like here in the ammonia, I put the lone pair on top. I could have put the lone pair here or here or here. It wouldn't matter because all of them are the same. I could just rotate the molecule and then it would go back to looking exactly like it looks now in this image. So tetrahedral, we don't have to worry about it. Trigonal bipyramidal, we do have to worry actually then about things like lone pairs and where we put them because we have these different position types. We actually have options of where lone pairs would go. And so that's why I was talking about kind of previously in terms of lone pairs, they're really the big piece. They're going to take up the most space. And a lot of that reason is because the lone pair of electrons, those electrons are on just that central atom. Any electrons in a bond, if they're shared between atoms, those electrons that are being shared are farther away from the atom itself. So they won't take up as much space because they're not as close to the atom itself. Is kind of the net effect that that's going to have. So when we have our trigonal bipyramidal starting electron geometry, what shapes can we actually get from that? Well, we can start with the easy one, right? 0 lone pairs, trigonal bipyramidal, nothing new there. There's no lone pairs, things stay the same. First lone pair. This is where things are important in terms of where lone pairs go. So we said that lone pairs take up the most space, right, more than a bound atom. So what ends up happening when we look at the shape for a trigonal bipyramidal geometry, if we want something to have the most space to spread out, it's a little strange at first because I think most people usually guess that the lone pair should go on top and bottom. But in reality, they actually always go in these equatorial spots. And the reason for that is it minimizes the smallest possible angles, which are what your biggest repulsions are, which are going to lead to things being not very stable. So if I put a lone pair on top, right, if I put a lone pair right here, there's 3 things that are 90 degrees away. But if I put a lone pair on an equatorial spot, there's only 2 things that are 90 degrees away. There's 2 more that are 120, but the 2 that are 120, that's a big enough angle, there's not many repulsions from that. So you're just trying to minimize how many 90-degree angles you have, because that's the small angle. And you do that by putting the lone pairs in the equatorial spots in this case. And so as a result of that, when we add our first lone pair, we put it in an equatorial spot. If we're trying to describe this shape, if you actually take this and maybe rotate it 90 degrees, what you actually end up getting is something that probably resembles like a teeter-totter or a seesaw on the playground when you were a kid. And that's actually where the name of this geometry then comes from. We refer to this as seesaw for the molecular geometry if the electron geometry is trigonal bipyramidal and there's one lone pair on the central atom. It'll always be then seesaw. All right. Our other possibilities, because we still have a couple other ones, if we had a second lone pair, again, both lone pairs are still in our what we call equatorial positions. So now the shape that we get is something that looks like this. This is the arrangement of the atoms. Again, if you rotate this 90 degrees, kind of spin it around to the right, you're basically going to get something that looks like a T. And so we actually refer to this then as T-shaped for the molecular geometry that we're looking at here. And if we had a third lone pair, which is kind of the most we can add to this shape, so imagine replacing this one with a lone pair also, all of the lone pairs are still in those equatorial positions. And now if we look at just the atoms, we actually get something that should look linear for its geometry. An example of this, triiodide, has a geometry like this. This is one of the examples that you've probably seen in lab last week and this week. All right, now, there's one more shape in terms of electron geometries for us to talk about. I'm going to back up one slide for a second here to get to this kind of image again for a trigonal bipyramidal geometry. So if I want to add a sixth area of electrons around my central atom, the biggest open space is actually between any two equatorial spots, like here or maybe between these two. I guess maybe easier to think about going between these two in terms of looking at the pictures. If I put electrons over here, this is going to get pushed over, this is going to get pushed over, and the end result is something that looks almost like a three-dimensional Cartesian coordinate system, right? With like an X, a Y, and a Z axis. Everything is 90 degrees apart. It's all really symmetrical again. All the positions are equal again. And there's always something opposite kind of any of those other outer locations. Now, it is a little strange because there's 6 things around the central atom, but we do call this octahedral for the geometry. Where that comes from again is the actual regular shape that you actually get when you enclose everything. If you have the 6 vertices here in this arrangement, you actually end up with what's called an octahedron for the 8 faces of that shape. And so that's where that octahedral name actually comes from this geometry. It's not the total number of things around the central atom. It's just kind of the three-dimensional shape that it creates when we have that arrangement. So molecular geometries. It turns out it's actually shorter for this one again because there's actually only a couple possibilities. We can have the 0 lone pair option, which is still octahedral, same pattern we've seen for all the other ones. When we add our first lone pair of electrons, it doesn't matter which spot we put them in, right? Because all these spots are equal. So if I put it on the bottom, or if I put it anywhere else, I can always rotate it to look still exactly like this. And now what I have is basically a square base of a pyramid that has one atom sitting up on top. And so we refer to this then as square pyramidal for that molecular geometry. If I add a second lone pair, now it actually does matter where I put it, right? Because I can either add a lone pair in one of these 4 spots, or I can add it on top. But if lone pairs take up the most space, it makes the most sense to try and space them as far apart from each other as possible. So the new lone pair actually will go opposite of where the first one was. And so if the lone pairs are opposite, the new shape is something that is now flat. It also looks square for its shape. So we call this then square planar. And it turns out this is actually our last molecular geometry that's a possibility. Octahedral, since you already have so many things around the central atom, you don't typically see more than 2 lone pairs on something that has an octahedral geometry. Or at least you certainly won't see anything like that in general chemistry. And so that's where kind of our different kind of arrangements for electron molecular geometry kind of ends. And I do realize it's a lot of different shapes, so I'll kind of summarize kind of quickly here with a table. This is one from our textbook. Actually, this might be an older one from one of our older textbooks. I think our current one is a slightly different version of this. But really, it is very systematic. So our general strategy, and I'm going to do a couple examples here in just a moment. Our general strategy is have a Lewis structure, and then what we're going to do with that Lewis structure is actually look at how many things are around the central atom. Once we know how many things are around our central atom, then we can go through and actually just count all the pieces of stuff as far as like how many total things are around. That's the electron geometry. How many lone pairs in the central atom. That'll help us figure out then the molecular geometry. So it is very systematic if you know kind of what those geometries are or how to get to each of them. And that's the tricky part. And so this chart here, it's actually 2 slides of a chart, is one way that you can kind of organize things systematically. And notice how over here It's basically like number of bonds, number of lone pairs for each combination. For the total number of charge clouds is what they called them in this table. It's the same thing as the electron groups, or just number of sites, things we've been talking about. And then you have your different molecular geometries that are possible based on, really, I always look at the number of lone pairs. You can also look at the number of bonds and treat it the same way. If you have 3 things around an atom and it's got 3 bound atoms, well, then you know it's trigonal planar. If it's only got 2 bound atoms and there was 3 things total around it, which only happens if you have 1 lone pair, then it's bent. And so you have ways of kind of doing that either by looking at the number of total bond, and I probably would specify, it says number of bonds, probably number of bound atoms is a little more accurate, just so that for our double bonds it doesn't cause any extra kind of weirdness or confusion in some of those examples. Right? You see this actually with CO2 up here. It's got 4 bonds, but it's really only 2 bound atoms because it has just the 2 electron groups around it, and so that's why it's linear. All right, so what I'm going to do now is kind of zoom out and just go through a few examples of like how do we get our different kind of Vesper geometries from our Lewis dot structures. And to do that, what I'm going to do is take a look at the same examples we drew Lewis structures for in the last lecture. So starting with, I think ammonia was our first example, right, NH3. And so now what we want to go through and actually do is assign our Vesper geometries. So to do that, we actually need our Lewis structure, which looked like this. Remember, that's how I drew it last time. And to identify our electron geometry, and I'm going to abbreviate here for electron and molecular geometries, just to save space so I can kind of fit all of this easily and hopefully still write it legibly enough for everyone to read it. So what we want to do to find the electron geometry is count how many total things are around the nitrogen. So we have 1 lone pair and 3 bound atoms for 4 things total. So 4 things around the central atom means our electron geometry is tetrahedral. Right? Now for the molecular geometry, we have 1 lone pair. That 1 lone pair is going to sit kind of on top, so that really if we just look at the atoms, we have nitrogen kind of sitting on top by itself, and then 3 hydrogens making a triangular base of a pyramid. So we call this trigonal pyramidal. Right? So there would be then our 2 electron geometries for ammonia. All right. If I take a look at then the next example I think we did last time was carbonate, CO3 2 minus. So Lewis structure for this guy. And when we have an example like this one that had resonance, in terms of the geometries, you can look at just one resonance form to figure out all the geometry information. You don't have to draw all the resonance forms to be able to really figure this out. Right? Because all the resonance forms are, for the most part, going to look identical in terms of a geometry. So which one you pick doesn't matter. You can just pick one, figure out your geometries. So I'm going to look at this version that I've drawn with the double bond going up. So electron geometry. And again, it's about how many things are all attached to the central atom. And in this case, there's 1, 2, 3 bound atoms and no lone pairs. So even though there's 4 total bonds here, there's only 3 actual areas of electrons that are spreading out around the carbon, right? So there's 3 bound atoms, and that's what we're counting here. So 3 things around the central atom means our electron geometry is going to be trigonal planar. And additionally, if we look at our central atom, there's no lone pairs. So no lone pairs in the central atom means that our molecular geometry is going to be the same thing. So our molecular geometry is going to also be trigonal planar. Right? I think the next example we had from last time was BF3. So for BF3, this one's a little more straightforward, at least in terms of the geometries. Right, that was our Lewis structure for BF3. So geometry-wise, electron geometry should look exactly like what we saw last time. There's 3 things around the boron, which means this thing should be trigonal planar again. And in addition, again, there's no lone pairs in the boron, so our molecular geometry is also trigonal planar. And this, like I said, this one's a little easier. There's no multiple bonds or anything crazy to have to worry about for that. It's more just the Lewis structure is a little strange because we had all single bonds here, and that boron doesn't have an octet. All right, next example then. I think we did the next one we had done was N2. Right, so we took a look at drawing its Lewis structure, which turned out to be a triple bond between the two nitrogens. So it looks like this for our Lewis dot structure. So our geometries, electron geometry, in terms of how many things are around our central nitrogen. And again, it doesn't matter which nitrogen we pick. Let's pick this one as our central one. There's one bound atom and one lone pair. That's two things. So that means our electron geometry is linear. And anytime our electron geometry is linear, our molecular geometry is also linear. Okay, take a look at the last one I think that we had drawn for our Lewis structure last week was sulfate. Right, and this is another one that had resonance. Just going to pick one resonance form to show here. It did have the, oops, that's a few too many lone pairs there, sorry. It did have an expanded octet that it used to get rid of formal charge, remember? That's why we have the multiple bonds here. So this was our sulfate Lewis structure for one resonance form with everything on it. So geometries, we're going to end up having 4 total things around our sulfur. Again, even though it's making 6 bonds, it's how many things are attached. We have 4 bonds. I'm sorry, 4 bound atoms, excuse me, which is going to give us a tetrahedral electron geometry. And then our molecular geometry will match that. Also be tetrahedral. Now, what I do want to take a look at, we've really only seen kind of tetrahedral, trigonal planar, linear out of these. So I'm going to add a couple examples for us to take a look at here. And we can go through kind of our steps for drawing Lewis structures as well, if we would like. So to do a couple more additional examples, let's do one of BRF3. Right, we did BF3 a second ago. Let's take a look at BRF3 instead. So for bromine and fluorine are both halogens, so they both have 7 valence electrons. So BF3 should have 28 electrons total for its Lewis structure. And if we draw our bromine, it's going to have 3 fluorines attached to it. Actually, I might spin this around just for the sake of being able to show off our geometry here in a second. So if I draw it like this to start, fill in my outer octets. Get to this. And if I count how many electrons, if I have 3 octets that are filled, it's 24. I started with 28, so 4 left over means 2 lone pairs on bromine. So that's a total of then all 28 electrons. Bromine does have an expanded octet here, but bromine, if we look at the periodic table, bromine in the periodic table, over here, it's down in the 4th row, so that's not a big deal. So bromine's perfectly fine being that far down on the periodic table, taking that expanded octet. So this is going to be our Lewis structure. Turns out they all have 0 formal charge. Right? Anytime a halogen has 1 bond and 3 lone pairs, that's a 0 formal charge. Apologize for the sound in the background. And anytime that and here for our bromine in the center, bromine in the middle, for its formal charge, we have 4 electrons in lone pairs and 3 bonds. So again, 7 valence electrons minus 4 minus 3 would be 0 for the formal charge in the bromine. So everything's good for this Lewis structure. So that's good. For the geometry side of things now. So for our electron geometry, now we have something where we have, if we count how many things are around the bromine, we have 1, 2, 3 bound atoms and 2 sets of lone pairs for a total of 5 things around the bromine, which means that this is now going to be trigonal bipyramidal, which is a lot to write out. So, oops, I apologize for a bit of a weird zoom there. Back to normal here. So you will sometimes see this abbreviated as TBP, trigonal bipyramidal. just for some shorthand, so that you don't have to write that one out because it is, I think, by far the longest one that we have to ever write for any of these different geometric shapes. And now for our molecular geometry, we again want to think about this thing's kind of general shape, right? I've drawn this maybe a little bit different in the orientation than it was before, so I can spin this a little bit if I draw it this way instead, so it's more similar to what we saw in our slides. And really what we're going to see is we have two fluorines in the axial positions going up and down, because remember, lone pairs always go equatorial. So we have one fluorine and two lone pairs in kind of that trigonal planar almost equatorial locations. And if we describe the shape now, here's if I spun it like 90 degrees like I was talking about in the slides, it looks like a T as far as the relative shape of all the atoms. So if what we actually end up calling this for our molecular geometry that we said is this is just T-shaped for the molecular geometry. All right, I'm going to do one more example to show off one that's octahedral to start, because we haven't really looked at one for that yet. Leave that there for people to see. So for one to show off octahedral, let's take a look at XeF4. It's a little strange. Xenon, if we're counting electrons, is actually a noble gas. So it actually does have 8 valence electrons is how we would count that. Fluorine, 7 each, like we just saw. So for total electrons, we'd have 4 times 7, which is 28, plus the 8 from xenon is going to be 36 electrons. We're going to have xenon as our central atom. 4 fluorines around it. Fill all the outer octets. If I have 4 octets, so 4 times 8 is 32 electrons to fill all these octets. And then what I'm doing is now I'm going to go ahead and add the last 4 electrons I have left, because I started with 36. I get 2 sets of lone pairs on the xenon. And this would be my Lewis structure then for XeF4. Now, geometry-wise, if we're talking about geometry here for XeF4, my electron geometry, I have 4 bound atoms and 2 sets of lone pairs, so 6 total things around xenon. So that's going to give me the octahedral geometry for the electron geometry. And then for my molecular geometry, I have 2 lone pairs. Right? And so those 2 lone pairs, it doesn't really matter where the first one goes, but the second one's always going to be opposite. So really, like this first lone pair that I'm kind of circling here is kind of going back behind into the page. This other one's coming out towards me, kind of towards us, out of the page. And so really what we're left with is something that looks exactly like it's drawn. It's flat. It looks kind of square in nature. And so we call this then square planar, right, for our geometry. All right, so that hopefully gives us kind of a quick rundown. And again, all of these examples where I'm assigning these geometries, especially these last 2, like if you're uncertain where that's coming from, like go back, we can check out our table, right? Like when we had 5 things around our central atom, that was the trigonal bipyramidal starting electron geometry if there were no lone pairs. But the example we looked at had a couple lone pairs, which made it T-shaped. That last example we just saw had 6 total things around the central atom. It had 2 lone pairs, so square planar was our final molecular geometry. So these charts, and there's similar tables in pretty much any textbook you ever look at. These charts, like that's kind of what we're using here. We're just looking how many things around the central atom. So that's bound atoms plus number of lone pairs. And then from the number of lone pairs that there are present, or if there aren't any, you can use that to go from the electron geometry to the molecular geometry. That's kind of our general layout and process.